So hello everyone and welcome to this next lecture. So this is one of the last few lectures of the Chook converter in the DC to DC converter lecture series, and in the previous lecture we had installed the latest version of the software with the Y zoom as well as the X zoom, and we had looked at how we can zoom in on some of the plots, particularly the capacitor plot, so that we can look at the exact fluctuations in the capacitor voltage. So in this lecture I'm going to finally implement the open loop control strategy so that we can check out how the converter behaves as we change the modulation index, or rather the duty ratio, from 0 to a particular fixed value. So as always, before I start this lecture, a quick update in the sense that if you are interested in these kind of video lectures but you want something a little more comprehensive, then I do have a full-length online course on Udemy. One of them is on simulating power electronic circuits using Python, and in this I cover some of the theory related to power electronics. I also talk about how you can install the software and how you can finally simulate circuits, ending with the simulation of a buck converter. So this is one of the courses. Another course which I have also using Python for electrical engineering is Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python packages to design, analyze and implement digital filters so that you can finally implement them in hardware. That's the purpose of this course. So if you're looking for something a little more comprehensive than what we are talking about in these YouTube videos, feel free to check out these full-length courses. So the link for these courses is provided in the description for this video. So I'll now continue with this lecture. So first and foremost, let us go back to our control page. So in edit control, we have only one control, which is the gate signal. So let's go over to my atom editor and let's check out this is the file. So I am now in the Chook converter directory, and this is my gatesignal.py file, which is also what has been added in the browser, right? Gatesignal.py. So in this gatesignal.py, I am setting the duty ratio, also called as modulation signal, to a constant value of 0.3. Now, in the previous lectures, I have increased it using another Python file. So for example, if you go to the buck boost converter, which was the latest one, we have another file called openloopcontrol.py. And in this file, we had changed the modulation signal from 0 up to a certain fixed value. So what I'm going to do is I'm going to copy this file over. So the first thing I'm going to do, go over to my file browser, go to the buck boost directory and copy the openloopcontrol.py file as well as the descriptor for this, that is openloopcontrol_desk.csv. So this is the descriptor file. So we copy both of these, come over to the Chook converter directory and paste it here. So now we have these two files. All we have to do now is add it to our simulation. So let's go over to the web browser and add this file. So I will choose the file, make sure I'm in the Chook converter directory, and choose openloopcontrol.py. And I'll just say openloopcontrol. I mean, you can give any description you want. I'll just keep it short. So this is now the file. Now the file is empty because when you create a file, it has no interface variables. So for that, all we have to do is upload our descriptor file, that is openloopcontrol_desk.csv. So we just have to upload it. This will not do. Remember, just clicking on it, it appears here. You must click on upload file to upload the variables. So now you see the variables appear. Now the most important variable is this variable called openloopcontrol modulation signal. So let's go over to the editor and see what's happening. So in the editor, I have this file and it is exactly the same as before. We are starting with the modulation signal from 0. So we can go over to the web browser and check it out. So you see the variable, the static variable is modulation signal, which is the same as this one, and that is initialized to 0. It is initialized to 0. We are increasing it by a very small amount, that is 0.001, and this increase takes place until it becomes 0.8. So at 0.8, we saturate it to a value of 0.8. So the modulation signal, or the duty ratio, however you want to call it, increases from 0 to 0.8. And this is assigned to this global variable open control modulation signal. And this open control modulation signal is a variable storage element, which means it's a global variable. So I can access this also in getSignal.py. So for that, all I have to do is comment out this line and uncomment this line. So I am setting my duty ratio in this file and I am accessing it in this file where I am doing PWM. So with this, we just have to go over back to the main page. And let's run the simulation. So as always, when the simulation is running, we go to the command line and make sure there is no unexpected error. So there is no unexpected error, which means the simulation is running successfully. So now that we are here, let us go and plot some values. So let's plot the output voltage. Okay. So we don't have to zoom in now. Let's plot the entire thing. And this is the output voltage. And this is the output voltage. So this is only expected. Remember, the voltage is always negative because a Chuk converter produces a negative voltage. And you see the voltage starts at 0 initially as we are increasing modulation signal, and now you see it is gradually increasing. Of course, we can plot it again and we'll see the increase even further. It's important to note that you can generate plots as the simulation changes. So it's encouraged that you do so to keep track of how your simulation is varying. So you see this is how the modulation signal is varying. It starts at 0, it keeps increasing negatively. So as the duty ratio increases, the output voltage increases. That's only expected. So, and we can plot it again. So let's plot something else for a change. Let's plot the currents. And these are the currents. So you see the currents also start with the 0. The important thing here is there is no huge spike in the current. And the reason for there not being a huge spike in the current is because we are starting with almost 0 duty ratio, which means initially the switch is turned on for a very short period of time. And because the switch is turned on for a very short period of time in the beginning, there is no spike in the current. Because remember, when the capacitor is uncharged in the beginning, if you turn on the switch for a significant amount of time, you will see a huge spike. So therefore, this is almost some kind of a soft start, right? So you see the current is increasing. Let's keep going. Let's go back and plot the output voltage, because now I think some kind of stability has been achieved. Let's go back, and yes, it has indeed arrived at a steady state. So you see, we are now going from 0 all the way to somewhere to minus 40. Okay, and now of course, since we have a zoom facility, let's go try that out. We can zoom. Okay, so we have the X zoom, which we don't really care about. We can do a Y zoom as well. So what that means is, let's do minus 42 to minus 38. Remember, always low to high, right? Even though it's a negative number, this start has to be lower than the stop. Otherwise it won't work. I mean, the plot will give back the entire plot. If you give an invalid range, it will just give you back the same plot. So this is our voltage. So you see, we are almost at minus 40.2 or so. I mean, you can go even deeper, but I don't think there's any need to. Around minus 40. So of course, let's go and verify it. We'll go over to our Excel sheet, and we know that the formula is 1 minus point D divided by 1 minus point D. Alright. And of course, let us put the value. The value here is 12 volts and we get 48 volts. Alright. So, of course, there will be some amount of drop, because remember, there are resistances in the circuit, there are other things in the circuit, so there will be some amount of drop, and therefore that accounts for around 8 volts loss. Of course, 8 volts is a significant loss, so it might be good to actually investigate this. Maybe we'll have to reduce some of the resistances. So this verifies that we have indeed got the voltage we want. Of course, there will be a negative sign here because we are not taking the sign into account. So let me go back and let me switch this off. So let's just go and plot some of the currents now. So now that we have the current plot, let's plot it again and let's zoom in a little. So we have plotted it, and this is the total current. So since we have achieved at a steady state, it would be advisable to just stop this simulation, because I think that is one of the reasons why the plots are taking time. So I'm going to stop it. You can let it run, of course, but here I would like to generate plots a little faster since I am recording a video. So let us zoom in once somewhere here, here and here, and let's analyze the response. So my first zoom will be from 0 to 0.05. Actually, that's a pretty big zoom, so maybe I should go from 0.03 to 0.05. We can always zoom in again. No, I'm zooming the wrong one. Okay, I will zoom in again. I should have zoomed in the current, I was zooming the voltage instead. So plot it. And let me go over, check out the current. Nah, it's too much. So I think we need only one. So what I'm going to do, I'm going to plot between 0.04 and 0.041. That should be decent. Because remember, we are switching at 10 kilohertz. So there is going to be several waveforms even if you plot for just 1 millisecond. So let's go over. Yeah, so this is my waveform. So here, of course, it will be beneficial if we zoom in on the y as well. So let's zoom in between -3 and +3. So it's 0.04, 0.041, -3 to 3. So this is currents, and now it's much more clear. So if we go and have a look, of course, remember there are scaling factors, which is why they are actually separate, but really speaking, these are actually waveforms superimposed on each other. The blue line is the inductor current IL1. The orange line is the inductor current IL2. These two are different, of course. And there is the green line, which is the capacitor current, right? So it's important to see how it actually works here, is that the green line is when the inductor current, when the switch is turned on, both inductors increase, right? Both inductors increase. The reason why both inductors increase is because inductor 1 is charged by the input voltage. Inductor 2 is charged by the capacitor, right? So the capacitor current is also increasing with respect to these currents. Only thing is, the current is in the negative direction, because that's how the current is charging. We have taken the capacitor current, this capacitor current, to be pointing in this direction, which is why when the capacitor discharges through the switch in the anti-clockwise direction, the ammeter current here is negative, but it's still increasing because the capacitor is discharging. And of course, when the switch is turned off, both inductor and both inductor currents decrease as well as the capacitor current, right? So this kind of matches up. Now let's go and plot it for another range. First, let's go and plot it all together so that we know which range to pick out. We just want to analyze the performance so that we make sure that everywhere for any kind of modulation signal, the performance is not very different. So now we plotted it for this small range. Let's go and plot it somewhere where this transient is happening, because it's an interesting peak here. So we know that this should be around 0.8. So let's go and zoom in for 0.8 to 0.81. This is quite normal because you have to sort of investigate where the interesting part of your waveform is. And the only way to do that is to successively keep zooming in on a waveform. Alright, so you see the currents are much bigger, which is why now we don't have to zoom in on the y-axis. But you see a very interesting result. Alright, now the currents are now very different, right? The input current, inductor current IL1, let me go over to the circuit. This current IL1 that is from the input side and this current IL2 from the output side are very different. This is a very interesting result. In the previous case, you thought they almost were merged together. You thought they were actually one current, but now they're very different, right? So let's see what's happening. As before, the performance is exactly the same. That is, when we turn on the switch, the inductor current IL1 and IL2 both increase, right? And that's normal. The reason is simple, because when the switch is turned on, the current input charges the inductor current L1 and the capacitor charges the inductor L2. In both cases exactly the same. And here too, you see the capacitor current is increasing in the negative direction. That's only expected. Now, what is important to note is, look at the width of this pulse. And the width of this pulse is what decides the difference between these two currents. That's why these currents are so very different. The reason is simple, because you are now charging your input current to a much larger DC value as opposed to the capacitor maintaining this current through the output inductor, right? This is the decoupling effect that you see. First, the input voltage charges your inductor current. Your inductor current charges your capacitor. Your capacitor then charges the output inductor. This is how the circuit is decoupled. This is why you see there is this decoupling effect in which there are two different inductors, right? But it's very important to note here, if you were to zoom in further and look at the difference in this current, that is how much the inductor current L1 increases and how much the inductor current L2 increases, the change is exactly the same. Alright, so which means in our case, of course, we've chosen the same inductor. We've chosen 1 millihenry inductor. But what that means is that the voltage that is applied across this and the voltage applied across this is exactly the same. Only then will you produce the same difference in currents. So this is one of the reasons why the Chuk converter is actually this is I would say again an advanced feature of the Chuk converter. We'll need more discussion if I need to go into it, but you could wind these two inductors on the same core because they have the same change in current. Therefore, the flux that they will be producing is also changing in the same ratio, and therefore they will not interfere with each other. That's the main concept here. So now that this is done, let's go back and of course plot it once again. I think we are more or less done because these were the two important zones of the Chuk converter. The only other zone is the steady state. We can just plot it just for the sake of completeness, but I think it's exactly the same. The performance, however, you see remains consistent. Whether we are in this transient or whether we are in this transient, the performance is consistent. So just for the sake of completeness, let me plot it somewhere in this range, 0.2. So I'll come down here and plot it for 0.2 to 0.201. And you see, this is exactly a similar plot. The plot is not very different. Only thing is, remember, the capacitor current has slightly decreased because it has now achieved a steady state, right? Therefore, there is in almost any converter, there is always some kind of an overshoot, and this was the case of an overshoot, right? So this is pretty much, you see, the performance is very similar to what we had before. It's just that the magnitudes are slightly different. I don't think it's necessary to explain it all over again. What's important to understand is, even though we've changed the modulation signal from 0 all the way to 0.8, the performance of a converter still remains consistent, right? And it's important to understand is that this, in such a state, is when you see the effect of the coupling capacitor. What an important role the coupling capacitor plays, because you see the difference in the energy levels of the two inductors. This difference in the energy level of the two inductors, this is accounted for by the energy in the capacitor. This is the amount of energy that the capacitor takes from the input and gives to the output. This is the decoupling effect of the Chuk converter. So with this lecture has already gone a bit too long. I'm going to stop this lecture, and in the next lecture we'll just wind down this particular lecture series by just cleaning up the code and eventually just making a few concluding remarks on this converter. So as before, if you have any doubts or if you are simulating along with me and something didn't work, feel free to comment in the video or send me an email or message me on social media, whichever is your preference. So with this again, goodbye for now, and I will see you next week where we will end the Chook converter in this DC-DC converter series, and after that we'll probably start with the SEPIC converter. So thank you so much and goodbye for now.